Thanks to Andy for the opportunity to speak. And what I'd like to tell you about is a project I'm doing at the moment in collaboration with Roland, Kevin, and Atul, all of whom are in the audience, about trying to find a top-down construction for celestial holography, but just in the restricted context of a self-dual theory. Self-dual Einstein gravity is going to be the bulk theory, we hope. Now, of course, just to set the scene, a lot of work in celestial holography has been bottom-up, has been trying to put scattering amplitudes that we already know from the bulk perspective in a basis adapted to null infinity or adapted to the celestial sphere, and see what properties we can learn by studying them. For example, what symmetry properties do they have? What really is the true symmetry group of quantum gravity? How these interact with known observable effects, such as memory effects. And of course, there's been a great success in doing that. However, if you want to demand that you've got an actual fully fledged duality between two independently defined theories, a theory of gravity or some quantum theory of gravity in the bulk that you understand, an independently defined dual theory living on the boundary, non-gravitational theory living on the boundary, that's a much taller order. Just to give one simple example of why that's immediately a hard thing to do, if you just try to sort of charge ahead blindly and say, well, for a theory of quantum gravity in the bulk, let's just take some string theory on Minkowski space cross your favorite Calabi-Yau or whatever, then in flat space, that'll perturbatively have a genus expansion. But unlike in ADS, where you can compare the string length to the length of the ADS, there won't really be an alpha prime expansion. That's just going to be a derivative expansion as a sort of effective field theory expansion. And we see that explicitly if you look at the structure of string theory scattering amplitudes in the celestial basis, work done by Tom, by Stefan, and by many other people following it up. So there, the overall alpha prime, which is kind of buried deep inside normal Veneziano-type formulae, it just factors out in the celestial basis. When you do a Mellin transform to put the amplitudes in the celestial basis, all the alpha prime just factors out as an overall power. And so there's no real expansion there. And these facts suggest, perhaps, that although you might expect that a dual theory still has a 1 over n expansion corresponding to the genus expansion, there really isn't anything that could play the role of a Tuft coupling. There's no dimensionless parameter in the bulk that you could match that to. And it suggests that the boundary theory might have to be inherently strongly coupled, not have a perturbative parameter like the Tuft coupling. Of course, that's not fatal. We know plenty of M-theory examples of ADS dualities that are inherently strongly coupled, but it certainly makes it harder. There are other questions that have been addressed, actually, or people have lots of interesting ideas about in talks that we've heard of, either over the past few days or perhaps this morning from Wei Song's talk. But for me, because top-down constructions of full gravity theory still remain very mysterious from a celestial point of view, I think it's good to have some simple toy models where we can explore these things in much more detail. And I'd like to suggest that these self-dual theories in 4 dimensions are a convenient set of toy models that are worth exploring. Now, typically, the sorts of models that we'll look at have BF-type actions. For example, in the talk of Kevin this morning, he had I think I've got my conventions wrong, this should be a B-, but anyway, there was some sort of BF action for self-dual Yang-Mills, and so there really is no Tuft coupling, again, just as I said before. In these actions, we could absorb it into the definition of B. We could rescale B by and absorb any coupling. But they're tractable, despite being sort of inherently strongly coupled, because they're also very simple. They're also integrable. This integrable structure can survive if you quantize it carefully enough at the quantum level, and that provides you with a lot of control of what these theories are. It also ties in very nicely with this rich structure of celestial chiral algebras that we see. Okay, so of course I'm not the first person to think about this. We've already got some very well-established examples, and these include Burns holography, perhaps the original example of Kevin, Natalie, and Atul, and examples related to what Kevin was talking about this morning that have largely been explored in the context of self-dual gauge theory, although certainly have gravitational sectors as well. And all of these these examples have in common that there are some combination of holography for the topological string together with some aspects of twistor theory. And just as an example, the original Burns holography, the bulk theory, starts out life as the B model in twistor space, so a topological string in twistor space. that's equivalent by Penrose transform to a theory of gravity, a slightly strange theory of gravity known as Mabuchi gravity in 4 dimensions. So these models treat R4 as a Kähler manifold. There's some preferred Kähler structure coming from the way the B model is set up. And this Mabuchi gravity is an action for the Kähler scalar. And then inserting a stack of D1 branes, not in space-time, but in the twistor space of this space-time, deforms the twistor space, that correspondingly deforms the space-time. And the space-time you get is an asymptotically flat space, and it's scalar flat everywhere, so it's got vanishing Ricci scalar, but not vanishing Ricci curvature everywhere. And it's known as Berns space. And then just like in standard ADS-CFT, there's a dual gauge theory which lives on this stack of ND branes. Here they're D1, so the gauge theory is 2-dimensional. And because we're in the topological theory, this gauge theory is chiral, because the B model's chiral. And there's a completely standard, really, holographic dictionary relating gauge-invariant local operators on the boundary theory to bulk gravitational states. And again, completely as standard, scattering amplitudes in this curved bulk. Despite the fact that the theory is integrable, on this curved background, these scattering amplitudes can be non-trivial, and at least a few of them have been computed, and they agree, as you'd hope, with correlation functions in this gauge theory. So the story of celestial holography for this Berns example is very natural. Right? It's very, very similar to standard ADS-CFT, and it suggests that. Hilbert spaces are not the same.
The Hilbert space of the dual is
not. I thought there was a matching between states. I mean, there is a matching between states, the Hilbert space states of the gravitational theory, the B model in twistor space, together with the states in the boundary dual. Is that wrong? Yes. I thought they were the same. Possibly in the large N limit, but I thought they were the same. And so it suggests a slogan, perhaps, that at least in this safe playground of self-dual theories, what celestial holography should be is something very similar to standard holography. It's just that the string theory is a topological string. It's a version of twisted holography. So the string theory in question in the bulk is a topological string, and it lives in twistor space rather than directly in space-time, so you have to use some version of a Penrose transform to figure out what this really means for celestial holography in space-time, as opposed to sort of standard holography, but in a twistor space version. Now, that's great. But at least in these examples, both the Berns example and the more recent examples, there are reasons to be a little bit unhappy with what we've got at the moment. And in both cases, the gravitational theory that you get on space-time ends up being slightly exotic. This Mabuchi gravity that you've got, I said it was a theory for the Kähler scalar, but this Kähler scalar obeys, in these theories, it obeys a fourth-order equation of motion. Correspondingly, this Berns space that we get, although it's scalar flat everywhere, it's not Ricci flat, despite the fact that we haven't turned on any other field. So it isn't a solution of the vacuum Einstein equations. It turns out instead it's a solution of the vacuum conformal gravity equations. And indeed, this theory is really best understood as a sort of Kähler subsector of conformal gravity. Furthermore, at least in the Berns example, to put the B model on twistor space in the first place, one had to introduce certain boundary conditions, introduce a divisor in twistor space, and this was, at least in the first example, done rather much by hand. And it wasn't totally clear there was a fully consistent string theory on that. I mean, it seems very natural construction to do, but it isn't completely clear that your string theory would really like those boundary conditions. Could be. We could ask. Maybe we'll ask later. Okay, so what I'd like to do today is to modify the B model in twistor space so that it really gives a top-down construction for Einstein gravity, of course still in this self-dual sector. Okay, so with apologies to people who already know about this very, very well, let me begin by reminding you of what you get naturally out of the B model and what we'd like to have from a twistor point of view and see how these things are the same and where they differ. So usually in the B model, you want the target space to be a Calabi-Yau. Traditionally, it would be a Calabi-Yau threefold, but we can certainly also define it on Calabi-Yau fivefolds. Kevin defined it as a sort of twist of supergravity in 10 dimensions, treating R10 as C5. And the closed string vertex operators will describe some sort of polyvector on Y. So there'll be some world-sheet fermions that become world-sheet scalars. Oops. There'll be some world-sheet fermions, eta and theta, that become scalars after. This is hard to control. That become scalars after the twist, and you can build vertex operators on the world-sheet by setting down as many of those as you like, really, and coupling them with some coefficients. And so these fields will correspond on the target space to naught p forms with values in some antisymmetric power of the tangent bundle, just depending on how many of these different eta and theta fields you choose to write down. And the most important one of these fields, certainly, is a Beltrami differential. So if we put precisely one eta bar and one theta, we'll get a field that transforms like a Beltrami differential in the target space. Now, on shell, those vertex operators obey an equation of motion, and the equation of motion is just this. And this is simply saying that your deformed d-bar operator, the standard d-bar operator plus your Beltrami, is a well-defined new integral complex structure. It squares to 0, just as it should. That's what this field equation is saying, so that you've got a deformation of the complex structure of the target space that's integrable. In the B model as a sigma model, that's all you'd find. As a topological string, there's an extra constraint on this Beltrami, which is that it has to preserve the Calabi-Yau volume form that you get. And that actually ends up just saying that you're deforming the target space as a Calabi-Yau manifold, not just as a complex manifold. Okay, so this constraint that it preserves the volume form is often said to say that this V has to be divergence-free, because certainly in the local coordinate patch, it just looks like the usual divergence of V. Okay, so that's what the B model usually gives us. Now, how about twistor space? So for flat space-time, four-dimensional space-time, twistor space is, as Kevin said this morning, 2 copies of O1 over CP1. So we've got some sort of Riemann sphere at the base of twistor space here. I was told I should point this at this. Maybe I'll try that. There you go. So this Riemann sphere at the base of twistor space, and then above each point on the Riemann sphere, we've got a 2-dimensional complex space, which are these O1 plus O1 fibers. Often I'll give the twistor space coordinate, the CP1 coordinates, I'll give it coordinates lambda, which are the same coordinates lambda 1 or z in the local patch that we use for the celestial sphere. And often I'll give these 2 fibers coordinates mu. So there'll be a mu1 and a mu2 that describe these fiber directions. And the relation to space-time is simply that points in space-time, for example, these red, blue, and green dots, correspond to Riemann spheres that are linearly embedded. So I've drawn them as lines here in the twistor space. And furthermore, we know just knowing about the intersection properties of these lines tells us about the light cone structure in the space-time. So if a pair of these lines happen to intersect, like this red one and the blue one here, that's telling you that the corresponding red and blue points in space-time are null separated. And in fact, in appropriate signature, the light ray that joins them is represented by this point of intersection. Now, knowing where all the light cones are, knowing where all the light rays are in space-time, is enough to tell you the conformal structure on space-time. It's enough to fix the metric up to a conformal factor. But it doesn't actually give you an actual metric. To know an actual metric, we'd in addition somehow need to fix an overall scale. So somehow we can say projectively whether or not two lines intersect, but if they don't intersect, there's no way of fixing a scale to tell us how far apart they are. I should say that at the moment I'm talking about points in C4, lines in twistor space being points in C4. Of course, we could impose some reality conditions on what lines we want to consider to get your choice of R22 or R31 or R4 signature. Now, the B model was all about deforming the complex structure of spaces. So if we deform the complex structure of twistor space, we'll get some new complex manifold. And because what is holomorphic now is different to what is holomorphic before, where the holomorphic lines are will now be different, right? Because we've changed what we think of as holomorphic. So we'll now get these other things that I don't know how liney they really are, but I've drawn them in pink, purple, and green here. And that will mean that the way the conformal structure, the way the light cones work in space-time has also changed. However, if we just deform the complex structure in some arbitrary way, again, that will mean that we've got some way of changing the conformal structure in space-time, but it won't give us any particular metric. And so what we'll get is, traditionally, we'll get a four manifold that obeys the self-dual conformal gravity equations, but not what we really want, which is the one that actually obeys the self-dual Einstein equations. This is a special case of the self-dual conformal ones. We get the special case, we get the Einstein equations, a vacuum solution to the Einstein equations, if we don't deform by any old Beltrami differential V, but if we insist that this Beltrami differential that we're using to deform our twistor space by is itself Hamiltonian. Why don't I try to use this? Is itself Hamiltonian? Okay, so it's instead of having two independent components, it's got three independent components because it's a vector in three-dimensional space, but maybe it's divergence-free in the B model, so one of those is removed by the divergence-free constraint. So in the B model, we might expect, in general, to have two independent components of our vector field, but actually we really only want one. We just want it to be some Hamiltonian function. And that really corresponds to the fact that in conformal gravity, there are two independent positive helicity gravitons, also two independent negative helicity gravitons. And for Einstein gravity, of course, we only want one positive and one negative helicity graviton. This Poisson vector that we're using to construct our Hamiltonian vector field is what we would also use to fix the scale on space-time. So some combination of this symplectic structure associated with this Poisson bracket together with a volume form on twistor space, some combination of those is weightless and fixes a scale.
Did your statement imply that in a generic soft-dual, conforming soft-dual net form, there's no way to fix the conformal factor to make it Ritchie flat?
I think that is actually true, that there doesn't have to be a choice of conformal factor that will make it Ritchie flat. But really my statement was that even if you're in a case where there does exist a choice of conformal factor such that it's Ritchie flat, the twistor space on its own, without this Poisson bracket, won't necessarily tell you about that. Even in flat space, for example, unless you know something about the background Poisson bracket, you don't know how to fix the scale to fix the flat metric. Okay, so, right, let's see what the task is. So if we're going to get self-dual Einstein gravity out of the B model, then we need to, first of all, to find a Calabi-Yau that's related to twistor space. Twistor space itself is not Calabi-Yau, so we can't just immediately put twistor space, the B model on twistor space. And then secondly, on that Calabi-Yau, we don't want to allow it to deform it in an arbitrary complex way. We want to deform it only in these special Hamiltonian ways. So let's put aside the first problem of worrying about how twistor space can be Calabi-Yau. Let's just pretend somehow we've got some Calabi-Yau, maybe call it R, with some local coordinates of Z, which perhaps will represent the base, this local coordinate on the celestial sphere, this base of the twistor space, and some other coordinates V, which perhaps represent locally the fibers. Okay. Now, actually, in the B model, we're in luck, because although I told you that the most important vertex operator there was this Beltrami, I said that actually you've got lots of vertex operators, at least in the standard B model, where you can put down as many of these different fermions as you like. And in particular, there's a vertex operator where you put down none of these eta bars, but two thetas, and that will transform like a naught form, but that transforms like a bivector, something we can use to build a Poisson bracket, which is what we need. Okay? There'll also be a B field, which will turn out to be conjugate to that. Okay, so this bivector, which is a field in the standard B model, looks promising. If we can somehow give this a vev of the type we need, that looks like we're heading in the right direction to get the sort of structures that we want for self-dual Einstein gravity. So let's see what happens if we do that. So the B model, the target space field theory, the string field theory for the closed B model is a Kodaira-Spencer theory. It has an action which looks something like this. Okay, so it's got a slightly strange-looking kinetic term. This kinetic term it looks a bit scary because of these D-inverse operators. But really, they're only, they look like they're non-local, and indeed they are sort of mildly non-local, as you might expect, because this is really a string theory, not a particle theory. But it's only very mildly non-local because the condition that these V's, also the bivector, was divergence-free means that these things exist, at least locally, right? There's a standard expression in any local patch for what you would mean by D inverse of V. So this first term here, the equations of motion of this are what we saw before that would say you've got an integral complex structure, and then you'd also get some equations of motion telling you that B and pi are holomorphic with respect to that new complex structure. But of course, because we're deforming the complex structure by a Beltrami field, the action is going to have some gauge redundancies, just saying that just general coordinate transformations, just smooth coordinate diffeomorphisms aren't going to change the complex structure in an important way. So we should quotient by those. And the structure of these BRST transformations, of course, depends on the structure of the action, because it has to be a symmetry of the action. Now, in the presence of a VEV, a VEV that's holomorphic, so the VEV won't appear here because it's holomorphic, but it will appear in this cubic coupling, and it'll give us a new term in the action if we just switch on a VEV, which involves this VEV in the cubic coupling, but now just looks quadratic in the remaining fields. In particular, if we choose this VEV to point up the fiber directions, these directions that I've put with dotted indices, then only the remaining direction, which was the Z direction in my local coordinates, will be left to contract into the 3 form. And so we'll just get a term that looks like that knows about the Z component of this vector field. Now, turning on that VEV has various effects. 2 of those effects are exactly what we want. First of all, this Beltrami component, and this component is the one that, in the twistor context, will correspond to the unwanted conformal graviton, the extra positive helicity state that you get in conformal gravity that we want to kill. This is now set to 0 by the equation of motion from B. If I vary B, there'll be a new linear term in the equation of motion, which, in the absence of other fluctuations, is just going to say that Vz has to be 0. Okay, and that's what we want. Secondly, because overall we had, as always in the B model, a divergence-free condition, that meant we've only really got two independent components of these vector fields to begin with. I've now just killed one of them, and so the divergence-free condition for the remaining one just says they're now divergence-free along their corresponding V directions, or in other words, they have to be Hamiltonian. They have to themselves be the derivative of something along these fiber directions. So that's great. We've killed the unwanted conformal graviton, and the remaining vector field has to be Hamiltonian, which is just what we wanted for self-true Einstein gravity. But unfortunately, there's a problem, because I've now changed the action, I've also changed the way that the BRST symmetries are working, because actually now they're symmetries of a slightly different action. And under the new BRST transformations, these components of V that we wanted to keep, these Beltrami components we wanted to keep, now have a BRST transformation that says this, and in particular, if this is the derivative of something, if this is Hamiltonian, then that something is just cancelling against B in BRST cohomology. I mean, that something is not BRST closed, and B itself is no longer BRST, B itself is BRST exact. Okay. I should say that similar ideas of turning on a background bivector were used by Kasher and Davide and collaborators in the context of chiral algebras for n=1 gauge theories, where they noticed a similar effect. But from the twistor point of view, this is terrible. We've killed all the components of the Beltrami differential. We wanted to just kill this unwanted conformal gravity, but we've actually killed all of gravity. And so back on space-time, what this will mean is we've got some theory that's essentially topological. It'll have no dynamical gravity in it at all. We've gone too far. In a little bit more detail, the reason we went wrong is that if you go back to the Kodaira-Spencer action, the unwanted conformal graviton part of the Beltrami and, let's say, the remaining independent degree of freedom of these vector fields were canonically conjugate. And the way BRST transformations work is that when one of these things becomes BRST exact, in other words, it vanishes on shell in the BV formalism, the other one fails to be BRST closed. So they drop out of BRST cohomology in pairs, and essentially when something bad happens to one guy, something bad has to happen to his canonical conjugate as well. They disappear together from the BRST cohomology. So that sort of tells us what went wrong, but it also tells us what we should do to fix it. Because to do better, what we need to do is find a version of the B model where these different components of the twistor space Beltrami, either the Z part or the V tilde, are now no longer canonically conjugate to each other, but canonically conjugate to some new copies of themselves that we didn't previously know about. So I'll explain what that cryptic comment meant in the rest of the talk, and I'll tell you about one way we've been going about doing this, but there may well be other ways. Okay. So the main idea is to start not on twistor space itself, but on some fivefold, which is going to be Calabi-Yau. Okay, so it is going to be a legitimate target for the B model, that fibers over twistor space with compact fibers. So we'll have some complex two manifolds that are the fiber over twistor space. Okay. It'll turn out that to get the total space to be Calabi-Yau and to fiber over twistor space, this fibration is going to have to be non-trivial in a way I'll explain, and that automatically gives vevs to fields, and that will automatically force our Beltrami differential on twistor space to end up being Hamiltonian in the way that we want. Now, because we're compactifying our complex fivefold down to twistor space, complex 3 dimensions, we'll have a Kaluza-Klein expansion. And normally when you do that, you'll get an infinite tower of Kaluza-Klein modes in the theory downstairs. But because we're in a topological theory, because we're in a theory that's purely holomorphic, there's really no metric on this space except in gauge fixing terms. And we can gauge fix, if you like, to make the size of this compact space as small as we like, and all the higher Kaluza-Klein modes are going to drop out. So the only thing, for these topological theories, unlike a sort of fully dynamical theory, when you do a KK reduction, you really only see the fibers through their zero modes, in other words, the cohomology of the fibers. And we'll see that we get lots of copies of all our fields down on twistor space, all valued in different parts of the cohomology of the fiber. And in particular, the pairing will pair the original Beltrami that we want to keep with some copy that's come from a different part of the fiber cohomology. Okay, so to do that, the way we're going to do it is we're going to start with a threefold X, which fibers over, not twistor space, but over CP1 with fibers that are at least generically K3 surfaces. Okay. So this CP1 is going to be the same CP1, the celestial sphere, if you like, or the base of the twistor space in the normal way. But we're going to add on some extra directions over that, which are these K3 directions. Now, this sort of K3 fibration has been studied a lot in the string theory compactification literature, but typically there, you want X as a threefold to be Calabi-Yau, because you're going to take that threefold and add on standard Minkowski space. That's not what we're going to do. What we're going to do is instead add on the remaining two directions of twistor space. So normally we had these two mu directions of twistor space fibering over the lambda directions, or this CP1. Now we've still got the same two mu directions, but they're going to fiber over the whole of this threefold. And now, if we want the whole space to be Calabi-Yau, so we can put the B model on the whole space, we don't want X itself to be Calabi-Yau, but instead we want the canonical bundle of X to be the anti-canonical bundle of the P1. We'll see in a bit more detail what that means and why that's the right condition in just a second. Okay, so in this complicated fivefold, we can still think that space-time bears a relation to this in just the usual way for twistor space. So it's still going to be the space of lines in twistor space, linearly embedded Riemann spheres in twistor space. It's just now that each line carries with it a whole family of K3s. Perhaps the important thing is that because we fibered the K3 not over the whole of twistor space, we've allowed it to vary only over the lambda directions, not over these two extra mu directions. We're treating the coordinates mu and lambda very, very differently. Now, conformal transformations on space-time, a conformal inversion in particular, would exchange mu and lambda. So the fact that this construction sort of explicitly treats them on a very different footing means we're going to be explicitly breaking conformal invariance from this construction from the very start. Okay, so let's see what this means in a little bit more detail. So for example, a large family of K3s can be described as quartic surfaces in some P3. This P3's got nothing to do with twistor space. It's some purely auxiliary thing. And I just take some generic quartic, so I set some combination of the homogeneous coordinates x0 up to x3 of this P3 to 0, such that all of these terms have got 4 powers with coordinates in them. And then there's a holomorphic 2 form on that K3, which is just given by the standard measure on the auxiliary P3, divided by this quartic, and take a contour integral, take the residue as the quartic goes to 0. Okay, so that's a single K3. To fiber that over P1, what we're going to do is just promote these coefficients, the coefficients here, to themselves depend on the coordinates of the P1. So now, of course, as you're varying around in the P1, as you're varying lambda, you're changing exactly which K3 you've got. You're changing the particular quartic you're considering. And that's giving you this fibration. And this condition that I said we needed, that the canonical bundle of our threefold should be the anti-canonical bundle of K1, that translates just to the fact that you want these coefficients to themselves be quartic in lambda. And the reason you want them to be quartic is we'll then get a Calabi-Yau volume form on the total space, which is the standard holomorphic form on twistor space that's got weight 4, times the holomorphic form on each Calabi-Yau. But on each Calabi-Yau, we're dividing by a different polynomial that's now got this quartic dependence in lambda. And so this thing will now have weight -4, balancing the weight of the twistor coordinates, so the whole thing is scaling invariant, which is the signature of it being Calabi-Yau. Okay, I should also point out that although generically, at some generic point over, some generic value of lambda, some generic point on the celestial sphere, the fiber will be a smooth K3. At certain discrete points, this K3 can easily, well, is forced to become singular, although the whole space itself will be perfectly smooth, at least as long as these singularities are not too severe. The whole space can remain smooth, so we've got a perfectly smooth Calabi-Yau five-fold target for our topological string. Okay, so at least away from these singular fibers, we've got an exact sequence. And what this means is that out of the directions we might move in our three-dimensional space, this X, we always know we've got a subset of directions, a subbundle, subsheaf, of moving purely in the K3 direction. So we know what it means to sit at a point in twistor space, a point in lambda, and move up and down the K3. But because moving in the P1 direction is only defined as a quotient, we don't know what it means to move in the twistor P1 direction, except if we can say we know what it means to move in the twistor P1 direction if we don't care whether or not that also means we move in the K3. And the reason for that is obvious. There's no way of saying holomorphically what it means to move in the twistor P1 without moving in the K3, because after all, the K3s are changing as you move along the P1, so you don't know how to identify them. And holomorphically, the fact that this is a non-trivial fibration, that we've got this condition on the total canonical bundle, means that there's no holomorphic way of splitting this sequence, of saying what it means to move purely in the P1 direction. Now, although there's no holomorphic way, holomorphically isn't necessarily the thing we really want, because we're trying to write down an off-shell string field theory, and off-shell, all our fields, our Beltrami's, were really just smooth functions. It was only on-shell that they obeyed some sort of holomorphicity condition. So off-shell, we should really be thinking of these as smooth bundles. And smoothly, we certainly can decide what it means to move purely in the P1 direction. For example, we know what it means to move purely in the K3 direction, so we just pick some arbitrary Hermitian metric on the total space. We always know what we mean by moving in the K3 direction. We'll just define that what we mean by moving purely in the P1 direction is just the orthogonal complement with respect to this choice of metric. But this metric was a Hermitian metric. We perhaps had to piece it together smoothly, so this is a very smooth thing to do. And of course, there's a price to be paid for doing that. The price to be paid comes in the D-bar operator. In the D-bar operator acting on this bundle, if we could split this sequence holomorphically, if we knew holomorphically what it meant to move in the two directions separately, then the D-bar operator would just be the diagonal combination of the normal two D-bar operators. The fact that we've got a non-trivial sequence means there's an upper triangular form, and this thing in the top right-hand corner is known as the Atiyah class. It's some cohomology class that cares about maps from the P1 to the tangent bundle of the P1 to the tangent bundle of the K3. And again, what it's doing there is pretty obvious. What it's saying is that as you move in the twistor P1 direction, you have to correct what you thought you meant by holomorphic in the K3 direction. Something that was purely holomorphic in the K3 direction at one point, i.e. annihilated by this operator at one point, isn't going to be purely holomorphic in the K3 direction at the neighboring point, because what you mean by holomorphic in the K3 has changed, because you changed your K3. And this alpha here is compensating for that effect. Okay, so when I wrote these slides, I optimistically thought this was already enough, thinking, oh, that's not very much, but I don't know whether you think this is a lot or not, but in any case, this is enough to see why we're going to get Einstein gravity without really needing to care too much about exactly what the K3 is and exactly which cortex we're using, etc. Okay, so let's see that. So I wanted to sort of stay fairly ambiguous about fairly ambivalent about whether I was exactly which version of the B model I was using. So let's just concentrate on the fields that are common to both. And in the closed string sector in something called the type 1b model, what we've got upstairs on our Calabi-Yau fivefold is our familiar Beltrami type object on the Calabi-Yau fivefold, but then another copy which knows about 3 antisymmetric powers of the tangent bundle. So it turns out that in this type 1b model, you're only allowed to put down odd numbers of these thetas that told me how many powers of the holomorphic tangent bundle we had. Okay, so as I said, smoothly, we can split the tangent bundle of X and also of this threefold. And it's going to be convenient to dualize the tangent bundle, the tangent sheaf to the K3 into its cotangent sheaf by contracting with the holomorphic 2 form that we've got, so lowering the vector index to a 1-form index using the holomorphic 2 form. But because our holomorphic 2 form scaled with lambda as we moved around, we get the identification not that they're equivalent, but they're equivalent up to some scaling in the twistor P1 direction. Okay. Perhaps I don't want to say too much about the details. I do want to say something about the details. But for example, now what we can do is let's look at this field that is sort of a Beltrami differential upstairs in the fivefold. Well, these 5-dimensional tangent vectors, they might split into a vector that's pointing along the twistor direction, or they might split into something that's pointing along the K3 direction, and then I'll use this identity to, I'll contract that vector field with the volume form to view it this way. And then I can similarly decompose these. They might have 1 or 2 of these tangent directions. These tangent indices might point along the K3 direction. Or 0 may, the bit where all of them point along the twistor space turns out to end up being non-dynamical, so I'll just drop it. And when 1 or 2 of them do, again, I'll dualize 1 or 2 of them using this trick, so I'll either get 1 or 2 powers of O minus 4. In particular, let me just point out that there's going to be this field here that's come from one of its tangent vectors pointing along twistor space, and 2 of them pointing along the K3, and I'll lower both of those 2 using my weighted volume form, and I'll get some field here. Okay, so these are still fields on our 5-dimensional space. I've separated out whether the indices are pointing in particular directions or not, but now I need to actually do the compactification to bring it down to 3 dimensions. And as I said, we won't get a whole Kaluza-Klein tower. We'll only see the 0 modes of those tower, which just know about the cohomology of the K3. And because I've because I dualize the tangent directions to cotangent directions, the right cohomology groups to think of are these. And on a K3, the only non-trivial part of that are the naught form, the holomorphic 2 form that we already met, its complex conjugate, and the volume form, all of which are 1-dimensional, and the H11s, which are via this contraction with the holomorphic form, telling me about the complex structure of my particular K3, and that's 20-dimensional. Y was the 5-fold. X is the 3-fold. Yeah.
So you say you do KK reduction and you get rid of all the KK modes. So then what's the purpose in life of the KK modes?
They have no purpose in the topological string. They're BRST trivial. I don't want them. They're bad. Really? Almost everywhere in string theory, people take a low energy limit to throw them away, right? I mean, here I'm saying it's not a limit. It simply is what you get in the topological string. Somehow it's not a surprise that the topological string only sees the deep IR. Maybe that's another way of saying it. Okay, so when we split our fields, for example, we had a Beltrami that in the 5-dimensional space Y happened to have its indices pointing along the twistor space direction. Now to reduce this in cohomology, we just have to look at how many of these, which of these cohomology groups it could contribute to. Well, it hasn't got any tangent or cotangent indices along the K3 direction. So the only thing that it could be is we could either take the constant in the K3, and then that thing will be constant on K3, so it'll simply be a Beltrami differential in twistor space. So instead of depending on all of Y, it'll only depend on the twistors. Or it could be that it's proportional to the 0-2 form, cohomology class on twistor space, the complex conjugate of that. And if you work out the details of that, that gives me some new field that I'll call phi, that again looks like a Beltrami on twistor space, but is twisted by, it's got weight -4. Altogether, we can go through the whole shebang. We can do that for all of the fields. This is what comes out. And in particular, descending from the Beltrami upstairs, originally, there's a bit which gives me a Beltrami downstairs on twistor space. That's the thing that's going to ultimately be my positive helicity graviton. But there's also a partner from that, which looks like a Beltrami, but twisted by weight -8. That was one of those fields that I said that had 2 of its vector indices along the K3, and we lowered both of them to get this weight -8. And then there's a bunch of other stuff as well. So if we just start with the Kodaira-Spence action upstairs and reduce it, plug in this decomposition, what you get downstairs is this. And let me draw your attention particularly to the first line. It looks more or less the same as the standard Kodaira-Spencer action that we had before for our Beltrami, except that it's now more of a BF type than a sort of Chern-Simons type. It's linear in this new copy of the Beltrami, this weight -8 copy of the Beltrami, V tilde, coming from the fact that that saw the cohomology of the K3. We still haven't said that V tilde at the moment is Hamiltonian. It's still going to give me conformal gravity as it stands, but I've at least got 2 copies. These other fields will correspond to a pair of axions, the phi tilde, and these psi's will give me some fermions. The most important term that I want to draw your attention to is this the term let me draw your attention to is this last term, which involves that Atiyah class, that off-diagonal part of the d-bar operator. So what is this doing? Well, again, that's taking in one of my Beltramis on twistor space and spitting out something that's in the cohomology of the K3 and being paired with something else that's in the cohomology of the K3, some of the other complex structure deformations of the K3. But importantly, because this thing was off-diagonal only in the twistor P1 directions, it was a map from, it's telling me how is my complex structure of K3 changing as I move along the twistor P1 direction. The only bit of the Beltrami it sees is the bit that's got its index along this Z direction, this P1 direction. That was the bit we wanted to kill. You can also view this as arising as some sort of combination of some sort of vev of the psi's, essentially, or some ghost associated to those fermions psi, arising from the non-trivial K3 fibration. So the psi's know about the complex structure. They know about fluctuations in the complex structure of the K3. But we've got some sort of background complex structure variation coming from the non-trivial fibration. And that's like a background value for these psi's. You can also view this term as coming from that. Well, the important point is this alpha thing is just purely about our background structure. So again, this is just some quadratic term in the action. And varying this field, this psi, will set exactly this Z component, the component of V that this Atiyah class sees, to 0. And as before, that will mean that the remaining components have to be Hamiltonian because of the divergence-free constraint. But because they were because we had this BF form of the action, the V alpha dots are no longer conjugates to the VZs, they're now conjugate to the V tilde Zs. So it's now the V tilde alpha dots that are removed from BRST cohomology. And the remaining gravitational fields are a Beltrami differential, which has to be Hamiltonian by virtue of the divergence-free constraint, so we get one positive helicity graviton, together with its canonical partner, and if you work through the details, that turns out to give you the negative helicity graviton. And again, one of each, as we'd want for self-dual Einstein, not for self-dual conformal gravity. In fact, if you take what we now know about these fields at the level of BRST cohomology and stick them back into the BF Kodaira-Spencer action that we had, what you get is exactly this action for self-dual Einstein gravity on twistor space that was first written down by Lionel and Martin Wolf. I think in view of time and my lack of expertise, I'm going to skip this slide. Maybe just briefly to say that this action, all the actions we talked about so far are chiral. And so, whenever you see a chiral action, its kinetic terms involve d-bar operators, not full de Rham operators, you might expect that there's going to be some anomaly associated with that in the gauge theory or gravitational theory. And indeed, they will have, as it stands, one-loop gravitational anomalies, higher loop gravitational anomalies, which in 6 real dimensions, 3 complex dimensions of twistor space will look like this box diagram. These will be cancelled in our full topological string. If we take the type 1 version of the topological string, then as Kevin and Sai Lee showed, there's a topological string version of the Green-Schwarz mechanism which will cancel that. Or we could take the type 2b model and we get some additional fields, and those additional fields would lead to a supersymmetric theory downstairs where the anomaly would again cancel. And once again, because this theory is having cancelled the anomaly, we'll have a theory that's well-defined at the quantum level and integrable at the quantum level. It'll be a little bit dull in flat space. It'll have no flat space scattering amplitudes. But in the presence of backgrounds, it can have some scattering amplitudes, and those will be interesting to compute. And non-perturbatively, there should also be lots of interesting effects as well. So it's far from a totally sterile theory.
There's more fields besides the graviton here?
Oh, yeah. So even in the type 1 so-called B model, there are these extra fields. These things will represent an axion on space-time. And there's some extra fields which will represent fermions on space-time, but in a non-supersymmetric setup. So these by themselves will not cancel the anomaly, and there'll be additional couplings in the model that I haven't talked about that will lead to a Green-Schwarz mechanism which cancels the anomaly. There'll also be gauge fields in the type 1 model, as you'd expect, right? There'll be open strings as well as closed strings. I think so. For the same reason, it'll be integrable. Modulo discussions that we have. If by contact light you mean the sort of discussions we have, then I know that there are, as you know very well. But putting that as most people would say there are no amplitudes. Good. Okay, so that's all really on the bulk side. Now let's start to think about trying to construct a holographic dual for this. So that's still something that's even more in progress, or even less in progress perhaps than what I've talked about so far. But it's obvious that what we're going to have to do is insert a D1, D5 system, somehow wrapping the threefold. So the D5s are going to wrap the whole threefold, that's the twistor line together with their family of K3s, and then we're going to wrap D1s just on the twistor line itself at some point in the K3s and at some point in the twistor fibers. And for that, it's important that we've actually got a section of this fibration, which will be true, for example, when the K3s are elliptically fibered. The details don't matter. What's perhaps important is that the way this D1, D5 couples to the closed string fields is determined entirely by something called its Mukai vector, which, well, the details are important, but for now, all you need to know about this is that it's some class in the cohomology of the K3. It cares about the cohomology of the K3 in a non-trivial way. And because it cares about the cohomology in a non-trivial way, it's going to couple to some field in the closed string sector that knows about the cohomology of the K3 in the corresponding non-trivial way, right? So they pair to give something that makes sense. Okay? And actually, it turns out that will correspond to giving a source for the axion field, not to the graviton, but it'll source an axion. So we'll end up with some profile. Out of this system, we expect we'll end up with some profile with a sort of logarithmic profile for the axion, similar to the sorts of things that Thomas and Bin have considered before and Stefan. This situation has been or very similar situations for not fibrations over twistor space, but for just a single T4 cross C3 or a single K3 cross C3 have been studied before, in particular by Natalie and collaborators. And they describe the deformed geometry that you get as some version of a superconifold. I think in today's language, what that means for today's talk, what that means is that you're not deforming. You're not giving a background to the graviton, the things that don't care about the cohomology of the K3. You're giving a background to the parts that did, in particular the axion. Okay, so what is the theory on these D-branes that we're going to get? Well, in the topological string, for example, for the D1, D1 strings, that's described, the open string sector is described by a field living on the D-brane, the D1 world volume, let me call that C, with values not in antisymmetric powers of the full tangent bundle to the Calabi-Yau that we had in the five-fold case, but just in those directions that are normal to the D-brane. Okay, so the boundary conditions on the open string set those thetas that are normal, whose indices point along the D-brane to 0, and you're just left with the thetas that point normal to it. So for a particular case, what that normal bundle looks like is this. So there are two directions here. Those are our standard two twistor directions, talking about moving where your D brane sits within twistor space. And then there are two further directions which tell you about how you might move your D brane within the K3. Okay, so the open string field contains the usual gauge field. That's when we take no powers of the normal bundle, together with a bunch of beta gamma systems corresponding, the gammas corresponding to taking one out of these four things, and the betas corresponding to taking the complementary three, describing transverse fluctuations in the branes. And then there'll be some further fields where we take pairs of the normal directions. Altogether, we'll get a world volume action for these D1 strings, which looks like a bunch of beta gamma systems. So there'll be some fields here, these mu's, describing fluctuations in the normal twistor directions. That's why I've also called them mu. And their partners are some new field, which correspond to the part of the string field that takes all the complementary three things. The beta and gamma r's here, they are the ones that correspond to fluctuations in the K3 directions. And then the rho and rho tilde, they're corresponding to choosing fields which pick two out of these four, in particular where I've picked one of these two O1 factors, so I've got an index telling me which one, and then one of the two remaining factors, and the rho tilde takes the complementary pair. Okay. Or I could have taken both of these two factors and complementary both of those two factors, that gives me this. Or I could take none and all four. This action is sort of similar to things that have played a role previously in various versions of twistor strings for Einstein gravity. And for those who care, let me just point out that you do get the rho tilde system as well as the sort of standard beta gamma systems. Okay, so this is just part of the action. There'll be further terms, of course, from D1, D5 strings. It's necessary to include some D5s as well as the D1s. If we're in the type 1 model, there'll be some space-filling O9s. There'll be some gauge fields, an SO32 gauge field associated to that. There'll be some further fields describing D9, D1s. I don't know what you get altogether. In the case of a simple product of K3 cross C3, this was studied by Natalie and collaborators, and what they found was that the resulting theory encodes is essentially the symmetric product orbifold CFT for K3, but not as a sigma model, but rather as a sort of beta gamma system. So you saw the chiral-Durand complex, if you like, or it was really the beta gamma system into the symmetric product orbifold rather than the full sigma model, as you'd expect in these holomorphic theories. And as usual, there's a standard holographic dictionary, which comes from just considering disk diagrams with a bunch of open string vertex operators around the boundary and a closed string vertex operator in the middle, telling you how my open and closed states couple to each other. And in the B model, this disk will localize to a constant map, so we'll just get a point-like interaction on the world volume of D branes. And just to pick two examples, of course, we can do this for any of our closed string states, but just to pick the examples we most care about, which is my Hamiltonian Beltrami V and the corresponding negative helicity graviton V tilde in the Z direction, the couplings turn out to be these. I could go through and explain the details of that, but maybe the most important point is really just that these couplings are known, they exist, there's a standard form for them, you can just work them out. Right? You're not guessing what the holographic dual is, the string theory tells you. Perhaps it's worth noting that if this involves the symmetrized trace of a product of these gauge fields, and so if the Lie algebra of the gauge group is semi-simple, which in particular in type 1 it will be, we'll need to have at least two insertions of the string field here to get a non-zero answer. And so we're going to need at least one of these alpha 1 dot indices, which means we're going to have to take at least one derivative of the Beltrami. And the Beltrami is already a derivative of the Hamiltonian, because the Beltrami is Hamiltonian. And that means that our Hamiltonian is going to have to be at least quadratic in the mu coordinates. In terms of, to translate that into celestial chiral algebra speak, it means we're not going to have any generators that correspond to standard translations. Okay? Only the higher modes of LW1 plus infinity as people are actually going to survive. And of course that's obvious. That's because we've stuck some D-branes in. We've broken translational invariance. We don't have that as a symmetry anymore.
So these extra gauge fields that you have, are they scaling up with also the flat space, or are they?
Which extra gauge fields do you mean? So if we do the type 1 in particular, if we do the type 1b model, then there are space-filling d-branes, which I haven't talked about, which lead to an SO8 gauge field in 4 dimensions. Again, they will have no scattering amplitudes, I think, in flat space, because it's purely self-dual. Well, in flat space with 0 instanton, etc. No.
Usually in ADS, you require some bullshit target.
Absolutely. Normally in physical string theory, you have to take a decoupling limit to get rid of the gravity. Because we're in the topological string, you're sort of automatically in the decoupling limit. So this phenomenon, I guess, was first observed or explained by Kevin and Davide. Or Davide, okay. There you go. Similar high level of authority. No. Importantly, because, okay, maybe that was my point in actually writing down this coupling. Because the origin of this negative helicity gravity, so the thing that would normally couple to the stress tensor is the part of the Beltrami that points along the d-brane. So the part of the Beltrami that points along the d-brane, I suppose I should use this, okay, which differentiates the open string field here. But because the negative helicity graviton came not from the Beltrami, but from rather its kind of weird K3 partner, it comes with some extra fermions in this superfield expansion. And that means that what you pick out of this term, even at the quadratic level, even if we drop all these higher derivatives, isn't really the stress tensor, but instead, it's this thing on the second line here. So the positive helicity graviton couples to, if I work out in detail what that previous coupling meant, it looks like that. These two states are very similar to states that I've seen before in various contexts of twistor strings. But the negative helicity graviton couples to some new state, which is not the stress tensor, because in the stress tensor, mu was, in the action, mu is canonically conjugate to some other field, pi, coming from some other part of the K3 cohomology. Here, this is purely built out of mu's. And as a consequence, the OPE between these two states dual to the negative helicity graviton is trivial, because the mu's don't contract with each other, at least at this tree level. Okay. So if you compute OPEs between these just at tree level, you get the standard L-Hamsi2, LW1 plus infinity algebra for the positive helicity gravitons. The negative helicity gravitons transform as module under that, as you'd expect. But the OPE between negative helicity, the open string operators dual to negative helicity gravitons is trivial at tree level. These OPs are just so far ignoring the back reaction of the branes on the bulk geometry, so we'll get some new bulk situation with this background profile of the axion that's been sourced by insertions of the branes. So these are sort of the vacuum case. They will receive planar corrections that deform this algebra to account for the D1, D5 system's back reaction, and they will also presumably, because we're in a non-supersymmetric theory, they'll also receive some quantum corrections, and at the moment I've got no idea what they look like. Okay, now finally, this dual theory should also see the non-trivial K3 fibration. How does that information feed into the dual gauge theory? Well, remember, all the fields, including these ones that know about the complex structure of the K3, correspond to some sort of local operator in the open fields. And I said that the varying K3 fibers in our background fibration could be understood as a sort of vev, a vev that depends on where we are on the twistor P1 for these fields, some combination of these fields. So what that suggests is that the operator that these couple to, which turns out to be a particular gauge field in this theory, sort of a gauge field in this theory, has some sort of background charge coming from this some Z-dependent, lambda-dependent background charge coming from the non-trivial structure of the fibration. Okay? Maybe that corresponds to turning on a Wilson line or some related objects for this type of gauge field. At the moment, we're still very unsure, but it's clear that this dual gauge theory will know something about the fact that we've done a non-trivial K3 fibration by some sort of background structure in the gauge theory itself. Okay, so I'm very much out of time. Let me just quickly conclude. We found a top-down construction of self-dual Einstein gravity in the bulk, coupled to a few other fields. Exactly what they are depend on the details or exactly which model you're talking about. And it's coming from working not immediately on twistor space, but rather on some Calabi-Yau fivefold that fibers over twistor space. This non-trivial fibration, in particular just over the twistor P1, not over all of twistor space, breaks conformal invariance explicitly, and that's what ultimately leads to this twistor description of self-dual Ricci flat rather than just conformally flat manifolds. We're hoping that we'll get a holographic duality for this by inserting a D1, D5 system, and hopefully there's a well-defined procedure which will really tell us what this duality is. It should work very much in the same way as normal ADS-CFT, except in this topological sector. And somehow this dual gauge theory should know about the non-trivial fibration, and I think it's coming through a background charge. Okay, maybe I'll just stop there. Thank you.